Hello, I am Taylor Brown, and this is the final for my circuits lab. Right now I'm on exercise 1, where we're supplying positive 12 volts through a 1 kilo ohm resistor, through a diode, and then connecting the diode to ground. So I've constructed that right here. I have my 1 kilo ohm resistor and my diode, and I'm using my DC power supply to give it positive 12 volts. And then for the first part, I'm just measuring the forward voltage, or the voltage through the diode. So I have my multimeter clips in parallel with my diode, and I'm getting a reading of 732 millivolts. So that's my value. All right, now I'm still supplying positive 12 volts to my circuit, but now we're measuring the forward current. So I just broke my circuit right here. I've just removed one leg of the diode and then connected my multimeter clips in series. And I am measuring a forward current of 11.54 milliamps. And I simulated about 11.4 milliamps. All right, now for the second part of exercise 1, I'm going to be supplying negative 10 volts to my circuit. So I'm just using my DC power supply to generate 10 volts, and then I switch the polarity of the clips. So now I have the ground clip going to the resistor and the power going to the diode. So now I'm going to be measuring the voltage across the diode, and I'm getting a measurement of negative 10.02 volts, and I simulated about negative 10 volts. All right, now for the second part of exercise 1, I'm going to be supplying negative 10 volts to my circuit. So I'm just using my DC power supply to generate 10 volts, and then I switch the polarity of the clips. So now I have the ground clip going to the resistor and the power going to the diode. So now I'm going to be measuring the voltage across the diode, and I'm getting a measurement of negative 10.02 volts. And I simulated about negative 10 volts. All right, now I'll be looking at the leak current from my diode. So I'm still supplying negative 10 volts. And to measure the current across the diode, I've broken my circuit and connected my multimeter clips in series. And I'm getting a reading of 0.2 microamps, or about 0.1. And I simulated negative 53 nanoamps, so they're both very small amp values. All right, now I'm on exercise 2 for the final, where we have our NPN BJT. I have my NPN BJT right here on my breadboard, and I have a 1 kilo ohm resistor connected to the collector, and then I have 5 2 kilo ohm resistors to make an equivalence of 10 kilo ohms, and I'm supplying that to the base. And then to the collector, I'm using my DC power supply. I'm using the fixed 5 volt channel to supply 5 volts to the collector. And then to my base is the varying voltage. So it'll either be -1, 7, or 2. Right now I have it at -1. Well, it's at 0.9. Now it's at -1 because I've switched the polarity of the clips here. So first I'll be measuring the collector current when the VN is -1 volts. And I simulated it to be about 17 picoamps, which is very small. And my multimeter isn't really able to pick anything up. So I'm just getting 0.1 microamps. All right, now I'll be looking at the collector current when the VN is 0.7 volts. So I'm supplying 0.7 volts now, and I've flipped the polarity of my clips back to normal. And my multimeter is giving me a reading of about 1.37 milliamps. And I did get a simulated value of 1.368 milliamps. Now I'll be looking at the collector current when the VN is 2 volts. So now I'm supplying 2 volts, and I still have my multimeter clips in series with my circuit to measure the current, and I'm getting a reading of 4.92 milliamps. And I did get a simulated value of 4.89 milliamps. All right, now I'm going to be looking at the voltage between my collector and emitter for different VNs. So first, I'm looking at when my VN is negative 1 volts. It's at 1 volts, and then I've changed the polarity of my clips right here. And so now I just connected my multimeter probes in parallel between the collector and emitter legs of my BJT. And I'm getting a reading of 4.95 volts. And I simulated it to be 5 volts. All right, now I'm on exercise 3 of the final, where we have an op-amp comparator with feedback. So right here, I have my op-amp, and I'm using this 100 kilo ohm resistor as my feedback. So I'm just looping it from the output back to the inverting node. And then I'm supplying the VCC with a fixed 12 volts, and I'm supplying a 5 volt reference to the inverting node, so to the second node right here. So now we're going to be measuring the output voltage as the varying input changes, and the varying input is connected to the non-inverting node, so it's this one right here. So for now, I'm supplying 12 volts to the op-amp, and I'm using the fixed 5 volts, and then this middle channel will be my varying voltage. So first, we're looking at the Vout when the Vin is 0, and I'm getting a reading of negative 552 millivolts. And I did simulate my values. I have this table right here. So up until about 4 volts for the Vin, it'll be about negative 500 millivolts, and then it will go up to above 10 volts. So for now, it matches the expected value. All right, now my Vin is 4 volts, and I'm still getting a Vout of negative 552 millivolts. So all of these were negative 552 millivolts. So when the Vin changes to 5 volts, that's when our change should happen, and we should be looking at a Vout of above 10 volts. So we'll see what happens. All right, now for a Vin of 5 volts, as expected, our Vout changed, and it is now 10.79 volts. And if we look at my simulation, let me use the cursor. At 5 volts, we are expecting about 10.4 volts. I'm getting a reading of 10.79. So it is pretty close to what we would expect.
Well, I guess let's see, but yeah.
All right, and now I've gone all the way up to a Vn of 10 volts, and I'm still getting the same output of 10.79 volts. So from 0 to 4 volts for our Vn, we got negative 552 millivolts. And then from 5 to 10 volts, we got 10.79 millivolts, which pretty closely matches the predicted graph here for the Vout when compared to the Vn.